Now we are going to get into the reactions of acids and bases. Okay, so you know about acids and bases, you know about the strength of acids and bases. Now we deal with reactions. So here's just a little review for you on what the different definitions are for acids and bases. For Arrhenius and Bronsted-Lowry, we talked about acids giving protons and all. Lewis acids are a little bit different, Lewis acids and bases, because they're dependent on electron pairs. So it's a little bit different. We use pKa's to help us if the reaction is going to work or not, because the pKa scale tells us the acidity, the strength of the acidity of the acid on the strength of the base, which we have learned all the criteria, so hopefully that should help us now. We should not have to look at the pKa tables, but I am going to use it in some cases to make a point. Okay, so first of all, the most important thing is, why does a reaction take place? Okay, why does any reaction take place? And in general chemistry, we talk about the fact that you need to go to lower energy levels, right? So the products will have lower energy. What about an acid-base reaction? Why does an acid-base reaction occur? And it occurs when the products are going to be weaker conjugate acids and bases. Okay, so if the products are going to be stronger conjugate acids and bases, reactions don't occur. Which is why we learn about the strength of acids and bases, so we can predict these kind of reactions. Because if you remember from when we were learning about the different types of acids and bases in organic chemistry, they don't look traditional. Okay, they look very different, and we have so many functional groups, and so in all those functional groups we have acids and bases. Okay, so how do we determine which one is going to be a strong one, which is going to be a weak one? When is the reaction going to happen? So if I write a reaction between an alcohol and an alkene, well, is that reaction happening? We don't know, right? So we have to have certain idea of how reactions are working. What is a stronger acid? What is a stronger base? Okay, so as we go on, keep in mind all those things. So here are some examples. Okay, so I'm going to start an example with just a simple inorganic acid base reaction. Okay, something that you have done before, so that you can see how the reaction is taking place. Now, I've been talking about reactions in almost all presentations and all the PowerPoints I've done, so it's not like this is anything new for you. Okay, but the more you do it, the better you will feel. So here is an acid, here is a base, and generally, without writing any arrows or anything except for the yield arrow, without writing anything, this is how you would write a reaction if you were in inorganic chemistry, is that acids will pick up a proton, become H3O plus, and then here you have the conjugate base, right? So that's what you form from an acid-base reaction. Here is an example of a typical acid-base reaction. HCl plus NaOH gives you salt and water, NaCl plus H2O. This here example is for an organic base and H2SO4 as a typical inorganic acid. Now, when you're classifying these two things as acid or base, you should know which one is going to be the acid, which is going to be the base, just by looking at them. H2SO4 is a mineral acid. Mineral acids are going to be generally stronger than any organic acid, or organic, well, base, of course, you're not going to compare it to bases, but it's going to be stronger than any organic acid. So which means that even if you were thinking, oh, I have an acidic proton here, sure, fine, you have an acidic proton, but this acid is way stronger, okay, than this one. So automatically this is the acid and this is the base then, which means this is the proton donor, this means this is the proton acceptor. Proton acceptor, where is the proton acceptor? Is going to be where the electrons are, okay, on the oxygen. So that's why you see here oxygen now has 2 hydrogens to it. Again, I haven't written out any bonds or anything. I'm just writing them out as reactions, because we are going to do the bond thing. We have to, all right, because without the bonds, we can't really clearly see what's going on. So I'm going to go through all that. So here is a little bit of detail for the mechanisms. Okay, so you can read all of this later on, because I'm going to talk about it right now. is here you have an acid and a base. Okay, so I've labeled them acids and bases. As you already know, hydrochloric acid is of course an acid. So which means the acid is the proton donor and the base is the proton acceptor. Now, what part of the base is the proton acceptor? Is it the hydrogen? Is it the oxygen? And it is the oxygen that is the proton acceptor. So which means that you will start your arrow from the oxygen to pick up the proton. And the second arrow is where the proton is giving its electrons to chlorine. And so you end up getting H3O plus and Cl minus, H3O plus from H2O getting the H plus. Okay, and the Cl minus is the leaving group, or sort of, what is left of HCl. Now, when you write something like this, the most important thing is where your arrow is starting from. Okay, so I color coded the arrows to show going from base to the acid and all that. But if your arrow is not starting from the right atom, it is wrong. So it should be starting from oxygen and not from hydrogen. It should be going to hydrogen and not to chlorine. Okay, because when you draw an arrow going from the base to the acid, not only are you showing that the acid-base reaction is happening, you're also showing what bond is going to form. Okay, so your arrow starting point and ending point is really important here. So if this is not sufficient for you, here I have shown you all of these things with bonds, okay, in there. Now, which one is better? Is it with bonds or without bonds? And really, initially, it is good with bonds, okay? So you can clearly see what is forming and what is breaking, okay? Eventually, we will get to this part also where you can show me this, the top reaction, provided your arrows are starting from the right place, okay? So here you can see that oxygen is picking up a proton. So if it picked up a proton, now oxygen has an extra proton. So now you have 3 bonds on oxygen, which is why it becomes the hydronium ion as shown here also. Oxygen is the one that has the formal charge of +1, not hydrogen. And then Cl is gone with the electrons that it has between hydrogen and chlorine, and so you get chloride. I know I'm talking in detail, but these things are kind of important, okay? And if you get your fundamentals correct from the beginning, then you'll have an easier time, okay, eventually. So this is a mechanism that we use, which means that when we say that we are using a mechanism, it means that you're showing arrows, okay, in there. No mechanism, just write an equation between acid and base. You don't have to show the arrows. But as soon as we say what is the mechanism of the reaction, you have to show the arrows. So here are a couple other reactions also. So I've taken an inorganic acid and inorganic base, so sodium hydroxide and HCl, and I'm showing you the pair together, one without the bonds, one with the bonds. Okay, now NaOH does not have a bond, as in like a line, because it's not a covalent bond. Okay, it's only an electrostatic bond. So it's an ionic bond, so we don't show that, right? So here you don't see that at all, but you see the line between H and Cl. So again, the hydroxide is picking up the H. Now this becomes water, okay? And the NaCl is gone, all right? NaCl is together now. So in this case, the bonding here, I'm not going to say it doesn't matter so much, but because a lot of this is inorganic in nature, and these are small molecules, so you're very comfortable with this, okay? You've written this reactions so many times before, but not with arrows though, okay? So this is how you would draw the arrows, the oxygen picking up the proton from the acid, and then the chloride leaving, but the chloride is not really leaving, it's there. It's still there in solution, and so you have the bond between sodium and chloride. Okay, here is the one for an organic molecule with a mineral acid, sulfuric acids. Sulfuric acid here is going to be the proton donor because that's the acid, and here is the methanol. So alcohol here is the base. Base meaning like where do you start the arrow? Start all the arrows from where the electron density is high. Okay, lone pair of electrons, negative charge, double bond, those are the places where your arrow should be starting. Go towards where there is low electron density, which is going to be, in the case of acid, a proton. Okay, so pick up a proton, and this is the product you get. This is how it would be if you were to show all the bonds. Initially, what I do for you, and you will see that in the practice sheets, is I've given you reactions like this, okay, where you can clearly see the bonding. So any kind of bond that is forming, any bond that is breaking, you should be able to see that. So that way you know how to draw your arrows. Okay, sometimes in structures like these, we can't see, what bond is breaking and what is forming. So here you can clearly see the bond is forming between oxygen and hydrogen to give you this kind of an ion. 3 bonds on oxygen. This is called oxonium. We'll deal with a lot of oxonium ion eventually. And then here, when you pick up a proton from sulfuric acid, then you're left with this ion, the hydrogen sulfate ion, HSO4 minus, and then this is the structure for the hydrogen sulfate ion. Okay, so this is the hydrogen that is gone, so there is negative here. Now, I didn't write all the lone pair of electrons. It will be too much, okay, because it doesn't really, in some cases, it doesn't matter. Here, it's going to matter because this is the base. This is the acid, so I'm not showing it here. Okay, so, and I don't expect you to show it. Even if you don't show me the lone pair of electrons here on oxygen, I'm going to be okay with that. It is good for you to write it. But if you don't show it and your arrow is going from oxygen, I'm okay with it. All right, so a little bit more about why acid and base reactions occur. So I talked about it before to you that the reason the acid-base reactions occur is to form weaker acids and weaker bases, and weaker acid-base meaning weaker conjugate acids and conjugate bases, okay, in here. So in all these reactions, you will see that I've given you the pKa. That way you can see how this reaction is working, okay? So for example, you have water reacting with an amide, NH2 minus, and once this happens, you end up forming hydroxide and ammonia. Now, without the pKa, you just have water reacting with amide, and you might write this reaction. But does this reaction really occur? Okay. So in order for you to figure out if this reaction really occurs, is you need to know the pKa's, or you need to know your strength of acids and bases. Okay, so I'm going to do both of them with you for this reaction. So that way you know the answer already, so you know how I'm working towards it also. So here is the pKa for water, which is 15.7. Here is the pKa for ammonia, which is 38. Very weak, right? Really, really weak. So don't look at both things. I mean, you can look at both things also, but focus on one thing. So acid giving you a weaker acid, okay, over here. The base also should be giving you a weaker base, which it is, okay. Amide is a stronger base than hydroxide. And if you're wondering, really, how did you know that amide is a stronger base? And amide is a stronger base because NH2 minus is coming from ammonia, whereas hydroxide is coming from water, which is a stronger base. Ammonia is the stronger base. You don't have to think too much about it because ammonia is a base. So this is a stronger base. This is a weaker base. Okay. So here we are looking at NH2 minus. So ammonia, this amide ion is coming from ammonia. So if this is a strong base, this is going to be even stronger because this is the negative of ammonia. Okay, so way, way, way stronger than that. And ammonia is a stronger base. So we're not looking at a stronger base giving you a weaker conjugate acid, because this is not the acid. This is a base. So it's giving you even a stronger base, okay, from it. This is a weaker base. Water is a weaker base, so it's going to give you a weaker conjugate base also. Okay, so right here you're getting a base. So you can think of these as acids if you want to. So ammonia and water, if you want to compare as acid, this is going to be a weaker acid. This is a stronger acid. Weaker acids will give you stronger conjugate base. Okay, so let me write that. Stronger acid will give you weaker conjugate base. So weaker conjugate base. Okay, right there it is. So that's how we know, okay, that we've got weaker acids and bases. So this is typically what I do. Okay, when I need to compare something, I will go ahead and figure out the acids and then work my way backward. Now let's look at the HOH. Actually, I just did that, right? HOH. So I did the water also, and I did the ammonia also. Okay, and so right here. Okay, that's what it is. So ammonia we know is going to be a base, right? And that's how we know that it was going to be a weaker acid, okay, in there. So we know that these are leading to both weaker acids and weaker bases. Okay, so let me now erase this so it doesn't bother us for our next problem. And let's look at the next one. Okay, in the next one also we are looking at alkyne. Alkyne is an acid that is being, the proton is being picked up by amide, again a strong base. And then here we have the alkanide ion. This is the conjugate base. And then this is the ammonia that is being formed over here. Okay, so is this reaction going to happen? This is going to happen because again you're leading to weaker conjugate acids and weaker conjugate bases. Now, one of the things I want to mention over here is that if the forward reaction is happening, the backward reaction will not happen. Okay, so if you had ammonia reacting with hydroxide, you will not get water and amide. It's not going to happen. Okay, and that's the whole point of why we're talking about this also, because we can predict then what kind of reactions will happen, right? So if your forward reaction is the favorable one, the reverse is not favorable. Okay, you learned that back in thermodynamics also. So the same thing is happening here. So if you have the alkanide ion and you have ammonia in there, you're not going backward because you already have the favorable products on the right hand side. So you cannot go backward in there. So anyhow, then the next one here, we are again treating the alkyne again with a really strong base. Now, alkane is a really strong base because alkanes, CH3, these are not even acids. You can't even consider them as acids because the pK is so high. So when we considered the sp2, sp3, these were the weakest acids, right? These were the strongest acids. So this is the weakest acid possible. So if anything gives you an alkane as a product, well, that's a good deal, okay, in there. So some of these things you should already know, like alkanes being like this, the weakest acids. Water can go anywhere, okay, because water is amphoteric, so that depends. Ammonia, your fundamentals should be for ammonia that it's going to be a base, okay, and that's how you work your reactions from there, okay. But this slide is just to show you that you get weaker acids and bases for favorable reactions. Here are some examples for Lewis acid and bases reaction, and Lewis acid base reactions are between electron poor and electron rich species. So electron rich would be the base, and LALB, that's the shorthand now that I'm using for Lewis acids and bases. And then here is the electron poor species, okay, and then you end up getting a new bond when the electron rich goes to the electron poor. Now, these electron rich and poor species, are they neutral? Are they positive? Are they negative? It depends, okay, because Lewis acid and base reactions are a little weird all the time. So you just kind of have to watch out for it, okay, and that's why I've given you some examples here so you can see the variety, okay, that we have here. So look at this one. This is a Lewis acid because it has a positive charge. This is a Lewis base. I mean, bromide, come on, like we don't even think of it as a base, right? But this is a Lewis base because it has extra electrons on it. So this electron pair goes to this carbon with the cation and it forms a bond. Okay, so here is the new bond that is being formed, and here I can highlight that for you. So right here is the new bond that is formed. In the next one, we have an ether. Hopefully you're comfortable now with your functional group. So here you can see that this is the ether. Ether is the electron rich. Boron is in group 3, and that is the Lewis acid then because it doesn't have enough electrons. So the oxygen gives its electrons to boron, and then you end up forming this new bond. Again, because boron took the electrons, it is negative. And then oxygen has given the electron, so it's positive, but there is a bond over here. That's why oxygen is positive also, because it has 3 bonds. Oxygen with 3 bonds is going to have a formal charge of +1. Okay, the last reaction that I have shown you is in a double bond. Okay, because I've given you all examples here. Okay, with an anion, with the neutral compound, and now here with the double bond. So double bond is picking up a proton here, like a normal, this is a normal acid, HBr, hydrobromic acid. So it seems like, yeah, it's a very, you know, very familiar acid for us. So it picks up this proton, and once it picks up a proton, the double bond is between the two carbons. So this hydrogen can go either on this carbon or on this carbon. Okay, so right now this is symmetrical. So let me just put it on the left side. That's what I decided, which means that this carbon now is the one with less electrons. So this one gets the positive. Okay, the Br is gone, and here is the Br. All right, by itself. So here the Lewis acid-base reaction is telling you, main thing that I want to tell you is that this is the electron rich, this is the electron poor. That's the main thing here. Okay, so keep your focus on where the electrons are for Lewis acid-base reactions. So here are some problems, okay, if whether a reaction is going to take place or not. So the first one is between acetic acid and potassium hydroxide. Potassium hydroxide, very good base, you know, acetic acid, fairly good acid, so no problem. This reaction is going to occur. Now, I just wrote here as in normal arrow, but usually with acetic acid, you have equilibriums, okay? But I'm not going to bother with the equilibrium right now. We'll just go ahead and write that the reaction is going to happen. Okay, how much? That doesn't matter. So I've colored coded the acidic hydrogen and the bases to show you a little bit, but otherwise I know you know, okay, what we're talking about here. Here is an alkene and here is water, and the reaction I've written here is no reaction. So let's understand this. Why this is happening is because alkenes are not really acidic. They're really weak acids. And then water is also a weak acid. Okay, so it's a weak acid, weak base. So such weak acid bases are not going to react. There is an electron-rich species here. There's an electron-rich species here, but the proton here is not something that this alkene can pick up. Okay, it's really, really weak acids. Now, how do you know that? You just know that. Okay, because there is no negative species here, there is no positive species here. And even though there was no positive species here in KOH, you knew that potassium hydroxide is a good base, okay? So there are a lot of things that you'll have to use your own information, your knowledge, your fundamentals that you have learned so far in order to write these reactions out, okay? Let's look at this one here. Alkyne, we know sp hybridized, there should be a little bit of acids in here, and NaH. So NaH, what's going on in here? NaH is sodium hydride. Okay, so which means that this is sodium plus and then hydride. So clearly we have a negative charge here. Now H minus, what is that? If you're classifying that as a base, then what is the conjugate acid? To find the conjugate acid, you need to add a proton. To add a proton to H minus, you will end up getting H2, which is hydrogen. We have not talked about hydrogen at all because we have not had a need to as an acid or a base, because hydrogen is not even considered like an acid or a base, which means what? If anything is not considered as an acid or a base, you're going to consider it as a weak acid. If this is a weak acid, this is a very strong base. Okay, it's a very strong conjugate base. This is a very strong conjugate base, then yes, it will pick up a proton. So that's what I have shown here for you, and then you end up getting H2. Okay. This sodium here, which is now bonded to, and I should probably, no, this is not a bond, this is a negative charge. So which is bonded to the carbon here, this is a counter ion, as we say, okay, and because the bond is ionic, okay, over here. So that is the third reaction. Let's see the fourth reaction. I think should be straightforward enough for us right now, because in this one, you have the minus here, which is very clear minus. And if this is the minus, this is the base, and then this should be the acid. So you look for the acidic proton, and this is the acidic proton. So you go ahead and pick up this proton, and then you end up getting the OH over here, and then this species is left without the hydrogen, okay, in there. Now let me talk just a little bit about this reaction. See if it is favorable or not. We wrote out the reaction, okay, but is it a favorable reaction or not? So in all of these, we haven't really talked about that over here. So the first reaction, let's see, okay, is it favorable? So here is your acid, okay, acetic acid, this is the acid, and then here is also the acid, right? This is the conjugate base. This is conjugate base. This is the base. This is the acid. The conjugate base is a little bit stronger because the acid is weak. This base is really strong, so which means the conjugate base is really weak. Okay, so this is the conjugate weak base. Weak acid, excuse me. Writing the right the first time. So for base, you have a very weak acid here right now. So which means this reaction is favorable because you have very strong acid base on the left-hand side. The second one, we said no reaction, so we don't have to worry about that. Okay. In this third reaction, let's look at whether this reaction is favorable or not. Okay. So in this case, we have a weak acid. We have a very strong base. I explained about the hydrogen to you. So if this is a strong base, the strong base will give you a weak acid, and then a weak acid will give you a strong conjugate base, right? So we have a weak acid here and a weak acid here. Hydrogen is a really weak acid, as I mentioned to you. So this reaction is favorable. All right. This strong conjugate base is not that strong because this is actually not very weak acid. I mean, it's a weak acid. So actually, no, I should take that back. Okay, I'm going to take that back, and I'll say that this is a weak acid. So which means this is going to be a strong conjugate base. Okay, so weak acid, strong conjugate base. But if you compare this base to this base, this is still weaker. Okay, because a hydride is going to be much stronger, okay, than this one. Okay, because that's coming from organic compound, and this was an acid, okay, to begin with. Hydrogen is not even an acid to begin with. Let's look at the last one, because the last one is a little bit different, because here we actually have two alcohols, right? You have an alcohol here and you have an alcohol here. You have an ion here and you have an ion here, okay, in this case. So here is the acid, here is the base, here is the conjugate base, here is the conjugate acid. Let's compare the two bases. When you're comparing these two bases, the stronger base is actually this one. The CH3CH2O- is a stronger base because you have more electron density here. This is low electron density. This is slightly more electron density. So which means that CH3CH2O- is a stronger base than CH3O-. So if it is a stronger base, then this reaction actually is not favorable. Okay, so I will write not favorable. It doesn't mean it doesn't occur. It does occur, but it's not favorable, so it's an equilibrium. Okay, and I didn't write that because yes, some of this reaction will occur, but because the product that we are forming is a stronger conjugate base, it's not going to be as favorable of a reaction. Okay, and that is how you figure out if a reaction is favorable or not, is by comparing the base strength or the acid strength, whatever you feel comfortable with, because on the right hand side, everything should be weaker. All right, so here is some problems for you, and this is to write arrows out. So I have written arrows out in the next slide. Okay, it's not on this one, so that way you can work on this if you want to, and then compare your answers with this one. So the main thing you should look at when you're doing acid and base mechanisms, and by the way, since this is your first introduction to writing mechanisms, please follow through properly. Okay, so look for the electron density. Here is the electron density. Okay, so this is negative. Look for the acidic proton. This is the acidic proton because it's connected to oxygen. So your arrow should be going from here to here. Pick up a proton And you can see that in the products because I've given you the products in this case. So you can clearly see that this is the oxygen that is losing the hydrogen. That's how you get the negative here. So you just have to draw the arrows. In the last two, I have given you an added challenge of not only writing the arrows, but also predicting the products, okay? Because you should be able to do that also by now. So that's an added challenge here, all right? So let's look at the So here are the answers then. So the first one we already talked about, the hydroxide picks up the proton and this bond breaks. So we already had the products given to us, right? So here is the negative, here is the water. So we only needed the arrows. Same thing here, if you look at the product, the Cl is gone away, so which means this bond has to break. And then there is a bond between OCH3 and the carbon, so which means that we need to go ahead and form this bond, okay, between the OCH3 and carbon. So that's that. Now for the next two, we also have to show the products, okay, to form. So really what we are looking for in this is which is the acid and what's the base, okay. So here the acid is HCl, very traditional acid, right? So that's the acid, which means this is the proton. So what are we looking for here? We are looking for the base, and the base is going to be the oxygen. So oxygen picks up the hydrogen here, and I can see that I have a little bit wrong here. So I'm going to go ahead and write it and I'll correct it in the PowerPoint. But this oxygen picks up the proton, so it becomes like this. You have the CH3. The Cl minus is correct, okay? And then so you have the O plus, okay, over here because now it has the extra proton, so it has a formal charge of +1, okay? So that's the product that's going to form. And then let's look at for D. D is a Lewis acid base reaction, so we have to identify what is the Lewis acid. So this is the Lewis base, this is the Lewis acid, because I know boron is going to be my Lewis acid always, okay? So look for electrons here. Electrons are on the oxygen, so that gives you the base over here that's doing the attacking on the boron. And so you form a bond between oxygen and boron. So the positive and negative, it's a good idea to write those because the positive is going to form because oxygen is giving electrons to boron, and boron should get the negative charge then, okay? So that is how these reactions are working. So you should be able to do both. And again, in the workbook, you're going to find that I have, more of these problems for you in there. And that brings us to the end of the chapter also. There's nothing much more to do in acid base except for practice, practice, practice. So do that and then let me know if you have any questions.